So hello everybody, thanks so much for coming back for the last day of the workshop. We have another full day ahead of us. It will be all about the science of deep learning, the science of meta learning, and we will start with a talk by Standa on the towards the science of deep learning, the loss landscape geometry. But before Standa starts, I have a few technical announcements. First of all, at the end of today, we have this session where we would like to put together some kinds of projects and collaborations with as many people that are interested as possible. So please come back to the session, and we also have 2 breakout sessions. So please use the chance to discuss with us and other people, what are the potential projects and the things that we would like to collaborate on. And then a recap of the fact that we are continuously searching for advisors and research managers, and the fact that we have put out those good diagrams. So if you haven't had a look at them, please do so, pass them on, and think about using them. So with that, I would like to hand over the word to Stanislav. Stanislav, thank you so much for not only giving us a presentation, but also coming here locally. So over to you.
Thank you, my pleasure. It's been a great, amazing lineup of speakers so far. Okay, so good morning, afternoon, and evening to people in various time zones that might be connected to the Zoom call. And thank you for inviting me to this workshop. My name is Stanislav, and I'm a PhD student at Stanford University, working with Professor Suryak and Goulet on roughly 2 main topics. One is the theories of deep learning, so understanding how deep learning works and bringing a scientific lens on how these really amazing systems manage to work so well on real-world distributions. And the second main topic I work on is applications of these insights into physics, mainly quantum computing and quantum state tomography, things like that. I spent the last year in Google research, working with mainly people from Google Brain and DeepMind on some amazing projects. And I'll base this talk mainly on 2 papers that came out of that period when I was in Google research. So it's primarily based on these 2 papers that are mentioned at the bottom of the slide. So the title of my talk is Towards the Science of Deep Learning, the Loss Landscape Geometry, which is the thing I'll be focusing on the most. And the papers I'll be discussing are mainly this first paper called The Large-Scale Structure of Neural Network Loss Landscapes that I was lucky enough to work with Stanislav on. You might notice we have similar names. I am the one in orange and he's the one in purple. He's currently a postdoc at NYU and he's moving to be a professor soon. It was published at NERDS 2019 last year. The second paper that I'm going to talk about and whose insights I'm going to bring into this talk is called The Deep Ensembles Loss Landscape Perspective. And again, I was very lucky to work with amazing collaborators on that, Clara Wei-Hu and Balaji Lakshminarayanan. Clara Wei-Hu was from DeepMind, currently still in DeepMind, and Balaji was in DeepMind back then and now in Google Brain. And if it's okay, I would start with a high-level introduction to explain why I think the problems I'm going to talk about are worthwhile to look at and why I think they're important to study. And I'll try to start a bit philosophically, if that's okay. I came from the physics background, so I have a kind of a scientific physical lens on systems kind of ingrained in how I think about the world. And in physics, we kind of have an observer and a piece of nature we're trying to study. And the observer is making observations about a system, measuring things, observing things. And here, the piece of nature is a cartoonish picture of a beach and waves coming in from the ocean. And the observer, if they're lucky, they have an experimental tool as well to poke the nature, to kind of make changes and observe what the changes do to the system. So they can actively influence the behavior of the system and observe what happens as a result. And they, in their heads or in the abstract space, they develop a model of how the system works with some objects and relationships between them. And so that's the way I kind of perceive how we do physics. And of course, this piece of nature has many levels of abstraction underneath. So this mechanistic level of waves and oceans and beaches as the fundamental concepts we deal with is not the most deep thing we can go to. We can go one layer deeper to the kind of mechanistic universe of Newton, and there the concepts and the phenomena and relationships are different. And since we're kind of wedded to the kind of philosophy of reductionism, we believe the deeper we go, the more fundamental the picture we have, and we can always derive the things from the deep level to the level above. So we believe that mapping is kind of many to one. So kind of going from these gears into the beach, there are many configurations of the gears leading to the same beach, kind of effectively. And of course, we can always go deeper. And now in this cartoonish picture, we can go to a quantum level of complex amplitudes and observables and unitary evolutions. And we could potentially go deeper still, but in physics, we don't really know what's there. So we don't know the most fundamental level. And so now we were going kind of deeper in the abstraction level, kind of into more fundamental, from which we could derive the upper levels. But deriving the upper levels is actually not as easy as it might sound. In principle, we think it's possible, and that's our philosophical conviction. But when you take the fundamental, let's say here, the quantum level, and try to derive the effective, the Schiller level, you should be able to do this with math, but it's super hard. And that makes it almost practically impossible if you traverse multiple layers of abstraction. And this idea isn't original. It's actually been around for quite some time, and it's well testified by the very famous essay called More is Different by P.W. Anderson, a Nobel Prize laureate in condensed matter physics, in which he argues that every level of abstraction kind of requires basically a new fundamental, and a fundamental is scare quotes, description of reality, because there the phenomena and the descriptions are kind of so different that it's impractically difficult to derive them from the deeper levels. So now, how does this relate to deep learning? So here is a Platonic description of myself as an observer of a system that's a deep neural network. Here we know literally everything about the most fundamental level of the system. We know the graph of the connections, we know the weights, the biases, we know everything about the system. And so me as an observer, I know everything about a system because I literally simulated on a computer, and I know to 32-bit precision all the numbers, and I can map every X to every Y or whatever my network does. Even if I wanted to, with a piece of paper and a lot of computational time or a computational machine, as we normally do. So we know literally everything about a fundamental level, unlike in physics, where we don't know the fundamental level. And yet, when we go to the high level of abstraction, so for example, we feed to a trained neural network a picture of a tortoise, and the network answers tortoise, we're still surprised, by phenomena we observe on these emergent levels, on these high levels of abstraction. And so, even though we know the fundamental level, we still are baffled by phenomena that can emerge from the myriad of applications of multiplications and additions we get by applying the weights and biases in the network. And what I'm trying to do in my research is, and I'm not the only person, many people have this approach, is I try to observe the neural networks as they are on this emergent level and build up objects and relationships and models of how they work on this level. Doing experiments with this cartoonish stick I have on in the picture, and trying to modify the networks in a way and see what happens. And the distinct advantage I have over, let's say, natural sciences here is that I know exactly how the system works, and I can do a lot of experiments. I have absolute control over the experiments. So I know everything, and I can do rapid experiments. So in some way, this is a way simpler thing than what we do with nature and trying to understand it through science. And yet it's pretty difficult, but strictly simpler. So now let me try to go back to the ground and describe what we are looking at in this talk. So I'm focusing on the science of deep learning, or the emerging science of deep learning, which to me is the study of emergent phenomena in deep learning that come out from the weight and biases applications, of which we know exactly what happens. And let's say studying the lost landscape that the neural network is traversing when it's training using gradient descent. And the general problem setup is pretty general. So we've got an image, let's say with classification, we've got an image mapped through a neural network parameterized by a weight vector W. So it's assignment of values to the weights and biases, eating the image, spitting out a vector of probabilities. And with a target label for that image, we can produce a scalar loss that tells us how happy we are with the decision the network made given the parameters W. And now we can study different pairs of objects in this setup. So here we can study the W, the weight vector, the description of the weight biases of the network, and how that maps to the loss, which is a scalar quantity telling us how good the network performs in our data. And I'll be calling this the weight space or the loss landscape. And we can imagine it as a landscape of hills and valleys where the weights, the individual weights, the parameters of the weight vector W are axes of this problem. There's an additional axis, which is accuracy or loss. It tells us how good our solution there is. And in this loss landscape, a solution is a position. A solution, by a solution, I mean a particular assignment of weights and biases to the network. So a particular mapping from input to output, a particular specification of the particular function from the class of functions we call neural networks, or the architecture we chose. And the origin here would be the place where all the weights and biases are 0. And then we can study a function space description of the whole thing, which is how the W maps to the actual vectors of probability. And so that's the actual answer the network gives on each image. So that would be, on this turtle, it would say, well, it's a 5% cat and 7% truck, and the others are 0, apart from a turtle, which is like 88, I guess. And so does the function space description. So the actual characterization of how the function reacts to data. And so this might be obvious, but just to emphasize it, equal loss doesn't mean it's the same function. So there's many functions that map differently on data that actually they're equal in how they perform in terms of the aggregate metric, which is the loss. And let me now go to the most kind of immediate, the most practical aspect of this talk. And to me, that's the most interesting as well. So now I'll describe 3 surprising simplicities that empirically we've observed in neural network loss landscapes. And I'll go through the 3 kind of surprising factors, surprising simplicities, and try to construct a model, a geometrical model that could kind of incorporate all these simple behaviors into a single thing and then make new predictions. And then I'll see what the consequences are of this model. Let's start with the existence of long directions in the loss landscape. And I'll be more precise in a minute. But now let's imagine a loss landscape in 2D where the height of a hill is the loss. And there's 2 directions. So we put weight direction 1 and weight direction 2 is a flat thing. And the height of the whole thing is a loss. And let's say we initialize our neural network here on the slope of the hill, just randomly, not at the bottom of the valley. And then we use gradient descent to roll down to an optimum. And here it's very clear, there's no obstacles along the way, so it just rolls down to the bottom of the hill. Now, if we were to connect the initialization to the optimum on a linear path, the linear path wouldn't be that different from the gradient descent path, because there were no obstacles the gradient descent had to flow around. Okay, that's an option that we have. This could be the case for neural networks. On the other hand, a more typical, at least based on some intuitive prior about functions, a more typical scenario could be there is an obstacle along the way to the optimum. And if that were the case, the gradient descent would have to go around to get to the optimum. And then the linear connection between the initialization and the optimum would be ragged. It would go up and down. It wouldn't be monotonically decreasing. And now the question is, and my default assumption would have been that this is the case for real neural networks, that the gradient descent does something crazy, something complicated, because it has to walk around obstacles along the way in the loss landscape generically. But I just ran a simulation myself a few days ago just to kind of verify that this is, the things I'm saying in the talk are actually correct. And what you're looking at here is color-coded the same way that you had before. So the thing on the left-hand side, the green curve, is the loss along the gradient descent path that the optimizer took in a 135,000 dimensional space, optimizing on CFAR10 with a CNN. And the right-hand plot, the purple path, is the linear connection from the initialization to the optimum, no gradient descent, just linear interpolation, and showing you the loss along that path. And you can see both of them are monotonically decreasing. So among these options, these cartoonish options, it's certainly not the option on the top, because you would see these bumps and non-monotonicity on the purple curve. It looks like more the picture at the bottom where the curves are similar. And that's extremely surprising because generically would assume there would be obstacles that the gradient descent had to navigate around, which doesn't seem to be the case. And so this, I'm not the first person to observe this, many people did, but to me, the first reference I saw in literature was by Ian Goodfellow and Uriel Vinolis at ICLR 2015 in this paper I'm linking at the bottom. But it's very easy to replicate, on your own experiment. I just ran this in 5 minutes. This, yes?
I have a question. So what kind of topology or architecture is this?
This is I think 5-layer CNN with some ReLUs and average pooling, and a very basic CNN structure. Yeah. So, I mean, of course, everything I say is given the experiments we ran and given the typical architectures, data sets, and optimizers we use. It's really hard to be kind of very specific empirically and also very broad in applicability. So that's kind of a fundamental trade-off we have to thread here. But a good question, thank you. Okay, so that was very surprising. Now, to an even more surprising fact about neural network loss landscape that actually got me into this line of research. And the conclusion will be that the solutions that are good in the loss landscape are densely distributed and almost everywhere. So they're easy to hit. Okay, so let's start from the basics. So we've got 3 axes, 3 weight directions, being our cartoon version of the high dimensional loss landscape. So there's W1, W2, W3, and the origin of the coordinate system. Now we take a point, which is, again, a configuration of the network, P, in the full space. And then we define a randomly chosen 2-dimensional hyperplane, or affine subspace, I think is the correct term, because it's offset by the P from the origin. And so this hyperplane has 2 dimensions in it, specified by the basis vectors θ1 and θ2, θ1 hat and θ2 hat. And the plane is also defined by the P. So 2 dimensions out of 3, it's not, doesn't contain all the points in this 3-dimensional space, just a 2-dimensional subset. And so we can force our optimizer to stay within the plane. Normally, we would be optimizing on a green curve, wiggling as we want in the full 3-dimensional space. In this case, million-dimensional space. In the actual case, it would be moving around as it wished. But what we can do here, and what we do as an experiment, is we force the optimizer to stay on this randomly chosen low-dimensional hyperplane. And surprisingly, if the dimension of the hyperplane is above a certain modest threshold, which is specific to the architecture and the data set, and it could be as low as a few thousand for CFART and a CNN. So out of the, let's say, 100,000 dimensions of the full loss landscape, if the hyperplane dimension is above a certain modest threshold, let's say 1,000, we can reliably find almost as good an optimum on that random hyperplane as we would have found in the full space, which is extremely surprising. So again, just to reiterate, you choose a random low-dimensional hyperplane, a random P, a random directions, and optimize within that, and yet you hit reliably a good optimum if the dimension is high enough. And that to me was super surprising. I thought, what kind of a distribution of points that are good would actually satisfy this kind of property, right? This is not something you would expect. If you imagine a locus of solutions that you have to hit and you have to navigate towards, you'll never hit that with a random low-dimensional plane. And so let's just go to some basic math. So imagine a 2-dimensional space and a line, and the line goes from infinity to infinity of dimension 1. And I'll call these things hyperplanes or affine subspaces, but they're just like straight objects of certain number of dimensions. So in a 2D, 2 lines of dimension 1 necessarily, apart from measure 0 set, intersect. And so there's an intersection of these 2 lines. In a 2D, they have dimension 1 each. Okay, now in 3D, these 2 one-dimensional lines do not intersect generically. They get, there's a point where they get the closest, but they do not necessarily intersect. In 3D, when you take a plane and a line, these things, and the plane is infinitely wide, and so is the line, it's infinitely long. So this is just a finite cutout of those things. There's an intersection generically, so they hit each other. And now in a d-dimensional space, we've got 2 hyperplanes or affine subspaces of dimensions dA and dB. And there's an intersection if dA plus dB is at least as big as the full D. So if the dimensions of these 2 planes add to the dimension of the full space at least, then you can basically be guaranteed there's an intersection if they're kind of chosen at random. And right, so those are kind of probabilistic statements, but generically these things are true. One can be more specific, but this is kind of, I think, a good enough description of the thing. Okay, so now imagine this scenario. Let's imagine that the loss 0 kind of manifold is an n-dimensional hyperplane or n-dimensional manifold submerged in a d-dimensional space. And this purple square is the manifold of good solutions. And imagine you start from an initialization, the red dot, that's not on this manifold, and the full space SGD, the same as the gradient descent takes you to that plane, and you get a solution that has a loss 0. Okay, so that's the normal situation. Now imagine that instead, we constrain our optimization to stay on this blue hyperplane of dimension little d. So if that, and so we have to stay on that hyperplane when optimizing, and we would like to hit this manifold at plus 0. So that only happens if the dimension of the kind of the hyperplane to which we are fixing the optimization, the blue thing, and the dimension of the red hyperplane, which is the place, the cartoonish place where we say the law 0 exists, then the dimensions have to add to at least the d, the full dimension of the space. And so this intuition tells us that in the previous situation, when we knew that we need only, let's say, 1,000 dimensions random hyperplane to hit a target in a 1,000,000 dimensional space, that means the target we're hitting is 999,000 dimensional. So because it was enough. Oh yeah. Okay. Let me answer later. This relates to yeah. Okay. So this tells us that the manifold we're trying to hit must be a really high dimensional. Otherwise, we would have hit it using a randomly chosen hyperplane. That's So that's really surprising. So I didn't expect this when I first got into this. So they're really high dimensional. And yet they're really hard to hit because they aren't full dimensional. So that's the kind of one of the paradoxes of high dimensional geometry, that even high dimensions are really hard to hit if they're not the full dimension of the space. So randomly choosing a point wouldn't get you to that hyperplane. You kind of need optimization to get there. And now the third surprising simplicity, which is maybe even the most surprising thing, is that optima seem to be all connected to each other. And okay, let me start from kind of the basics. Imagine the origin, there's the blue dot, and two initializations, those are the green dots. And there's and so from the initialization 1, you optimize and get to optimum 1, and from initialization 2, you get to optimum 2. Because the way we choose initializations, let's say Xavier initialization or the He initialization, and you do Gaussian measure concentration, in high dimensions, Gaussian distributions are basically the same, like L2 norms. So there's a concentration of all the measure into a shell of a certain thickness. And that's the reason why we basically find all the initializations lying roughly the same distance from the origin. So the same L2 norm of the weight vector. And their angle is roughly 90 degrees. So they're roughly orthogonal, again, because they're randomly drawn from a very high dimensional distribution, IID. And so when we optimize, we find that when we optimize the same way, the same number of epochs, learning rate, all the hyperparameters fixed, the motion that we undertake in this lost landscape is roughly equivalent. So the distance we travel is roughly the same in L2. And this orthogonality empirically is preserved when we optimize. So we kind of move in orthogonal directions. So that doesn't mean we kind of know where to move, but after the fact, we can kind of check and see that it's roughly orthogonal even after. And of course, the optimum we hit isn't an optimum, it's not a single point. So there'll be in its surroundings in the weight space kind of slightly worse optima, and the further you go, the worse the optimum, the worse the solution is. So the lower the accuracy, the higher the loss. And so we've got these two blobs, kind of the basins to which we navigate it, one containing the optimum 1 and optimum 2 on the other side. And if we were to walk on a linear path from the optimum 1 to the optimum 2, we would find that in the middle, in the weight space, in the middle, the solutions are really bad. So they've got a high loss and low accuracy. So from that point of view, on this kind of section, it seems that the optima are not connected. And this is a real picture of a lost landscape of a real neural network, the overall neural network. The origin is the aqua dot. The two initializations are projected into this plane. Those are the purple dots. And the two green dots are the two optima. And the plane is defined by the origin and the two optima. And then each point within this plane is colored based on what accuracy we get there. And you can see that this is basically corresponding to the picture I showed before. There are these two basins in which the optima live, and they don't seem to be connected in the middle. But now the question is, could I find a path that goes from one optimum to the other optimum, such that I would not get to a bad loss place along the way? Could I optimize such a path? The linear one isn't it, but could I find it? And it turns out that the answer is yes. And two papers last year managed to find them using quite complicated methods. And later in my follow-up paper, we found a very simple method that allowed us to diagnose something more about the geometry of the optimized path. But the very surprising thing is that these optimized paths exist, and every pair of basins we tried, they were connectable using these paths. And so the modes are connected, but the connectors are really hard to find. So by randomly searching, you wouldn't find them. By randomly guessing a kind of dimension in which you bend the path, also you wouldn't find it. You have to optimize for it to find it. And then it's really interesting. So the plots at the bottom show you The x-axis is the interpolation coefficient along the path, the black path and the optimized orange path. You can notice on the left-hand plot that the loss along the black path, the linear one, goes up and down, so in the middle it's high, but on the orange path it stays at a low value. The same for accuracy in the middle. But a more surprising thing right now is that how the labels the two functions predict on the test set are similar to each other along these paths. So you look at how the function along the optimized path changes as you go, and you characterize it by looking at the test set. And you notice that as it's moving from the blue basin, it's kind of the blue quality of the function is kind of fizzling out until you hit the middle where it switches to the kind of red character of the function. So it really seems that you have these kind of two basins, and in the direction of the optimized path, they're kind of extended all the way to the middle where they meet. And there they kind of switch the functional characteristic. And so we build up this kind of mental model of what's going on, where we have the origin and these kind of two big basins, manifolds manifold 1 and manifold 2, these manifolds kind of being the loss 0 or low loss below epsilon manifolds. And these things are kind of tilted into the page or into the slide, and the linear path, which is the black path, wouldn't take you within the manifolds, but if you were to walk on the orange path, you would be able to traverse from one to the other, as we do when we find such a path. And these manifolds we visualize as kind of pizza wedges radiating from the origin. This radial direction is there because for a softmax loss, the only way you can get to loss 0 is when you drive all the probabilities of the wrong answers to 0 and all the correct answers to 1. And to do that, you need to take the logits to either plus infinity or minus infinity, or their differences. And to do that, you kind of need to rescale the weights such that you multiply the input signal to make them as big as possible. Provided you're correct, you drive the loss to 0, but this corresponds to moving in radial directions in the loss landscape. So that's why you've got this flat radiating character of these pizza wedges. And there, just to emphasize, there are many more long directions, many more flat directions within these pizza slices, within the good solutions, the good solution manifolds, than there are of these short directions, which are the aqua directions there. The aqua directions would be the 3000 short directions we need to compensate for by the low dimensional cutting plane in the surprising fact number 2. And the long directions are the ones in which you can move a lot and you won't jeopardize your loss all too much. And so again, this is the same thing I talked about. When you're moving on a black path, you can go to high loss and low loss. But if you were to move on this optimized path, it would be, you would stay on a good loss and you would switch the functional characteristic in the middle. And so there's like different measures of similarity of functions that the one can employ. We chose the fraction of labels that are different. And so you could ask, where is the initialization with respect to this wedge? And so you can imagine it's kind of outside of a pizza, and initially you kind of glide into the pizza, the good manifold, and then within that you kind of move more simply. And this is a picture from a so far unpublished paper where we show that what you're looking at is a plane defined by 3 points in the optimization trajectory. The initialization, that's the ball on the left. The cross is epoch 1, and the star is epoch 10. And the more red, the better the accuracy. So you can see that you kind of go in and then you stay within it. So that's kind of equivalent to the cartoon on the left. And so what I just described is just repeated in this GIF, which I'll probably do. I have good time. Okay, so this is basically the construction I was describing right now. And so you have these manifolds that kind of touch in the middle. But if you were to walk linearly, you would have to leave them, but you can find a path between them. Okay, so now let's go back to this picture of the loss landscape on real networks. And you can see again these basins that seem to be disconnected. To see them connected, you would have to follow the path by this plane. It wouldn't be a linear cut. And then you can also look at the similarity of the functions on this slice, and you can see that on the left-hand side, the color is a similarity to the blue optimum, and on the right-hand side is a similarity to the red optimum. And you can see that in the red basin, the functions are similar to the red optimum, whereas in the blue basin, the functions are similar to the blue optimum as as expected based on the cartoon picture. And so this is just the two things together. So the basins seem to be both good, but they're quite different in their predictions. So in the loss landscape, they're pretty equivalent. In the function space, they're not the same. And so this is crucial because when we are, let's say, combining solutions to form an ensemble, we want the answers to be as different as possible, but also, being both good, such that we get better estimates of the true answer when we combine their probabilities together. And so let's see what would happen if we bend the slice into the page. And so this is a kind of an intuitive picture that, that we produced. And so the dots along the path are the points along the optimized trajectory between the two green optima. And this planar section is actually not planar, it's bent into the page. And each dashed orange line is a stitch between triangular sections of this thing. So it's kind of bent into the page. But you can see that you can move from the green optimum on the top to the green optimum on the right, with your feet dry. You don't have to go to any bad areas along the way. And it's all dark there. But as described before, on the right-hand side, you can see the functional similarity of these functions. And you can see that it's kind of reddish until the middle, after which it switches to a blue-like function and continues to be so until the optimum. So that's kind of describing this touching of the pizza wedges I showed at the cartoon before. Or just the detail of this picture. You see that it kind of goes into the middle and there it fizzles out in terms of the similarity. And now let's go to the practical implications of this. I think this model is really interesting. And so we build it up using these kind of simplicity observations and try to predict new phenomena. And some of them we predicted and verified in the paper. The first one, the large-scale structure of neural network lost landscapes, which gave us confidence the model is describing something real about the lost landscapes. Of course, it's a highly idealized model. For example, the main weakness is that directions are not either long or short, they're anything in between. But if the separation is big enough, you can put a partition somewhere in the middle and effectively it behaves as long and short directions. So that's one thing that can be improved upon. And so let's look at the practical implications, and in particular, let's study the Bayesian kind of implications and implications for ensembling. So when you start at initialization 1 and optimize to Bayesian 1, and I made the trajectory very wiggly, but even though we saw it's pretty straight, we go to the Bayesian 1 where the optimum one lives. And we could sample the points along the way, and we can kind of compare how they answer on the test set. And we can try to cluster the predictions, let's say using t-SNE on the predicted vectors of the test set and see how similar they are to each other. So in this plot, I not only have a blue initialization going to a blue optimum, but also a green initialization going to a green optimum and a red initialization going to a red optimum. And the dots along the way are the different epochs of the optimization for each blue, green, and red trajectories. And I turn the picture, the plot, around to kind of align it with the cartoon. And you can see that as you go to the optimum, the blue dots are kind of similar to each other. So their predictions are similar to each other. Just to emphasize, the thing on the left-hand side is a cartoon of the weight space picture, so the configurations, whereas the picture on the right-hand side is the answers the function gives. So it's actually a functional space we're describing here. And we're clustering it using t-SNE. And we also use more quantitative ways of characterizing this that I won't get into, but the t-SNE is very visual in this. And so if you were, so what you could do is you could get to this Bayesian and start sampling around. But a problem would be that these functions you would sample in that Bayesian would be very similar. Their answers would be very correlated to the optimum you got to. And that's just the picture I showed before. It's kind of spreading out as the epochs increase, and you see that the functions are similarly answering the blue kind of epochs of the training, the red ones as well, green ones together as well. But then we start exploring the neighborhood of the tip of the optimization trajectory randomly, and I'll put stars there in the GIF. And you can see that the neighborhood functions there are also similar to wherever they ended up. So their predictions are similar to the optimum around which we're exploring. So you're around your weight space position in the weight space, but also in the function space, you're kind of in the neighborhood. So that exploration doesn't give you as diverse a set of functions as you could hope for. Right. And so just as a conclusion, between optimization trajectories, things are very different, but within the trajectory, they're quite similar in their predictions. And so how can we deal with this? So if we want to combine predictions well, we can start with the simplest thing we can, a vanilla ensemble. We start with two initializations. We'll go to Bayesian 1 and Bayesian 2 for the two different optimization trajectories. There we get a single point estimate of the function, and then we average their predictions. So we ensemble their predictions, and we can average the predictions or average the logits. There's different ways of kind of combining them, but effectively we combine these two prediction vectors. And that star doesn't lie anywhere, or possibly somewhere, but we don't know where, in the weight space. Because that star is a combination of two models that are 2 points in the weight space. So that's why I lifted the star above the page. And this is kind of the typical ensembling thing that we very often do to increase the performance of our model. What we can do instead is we can get better optima, better estimates of the actual center of the basin by having a bunch of estimates there. And it's been known in literature for a long time that in convex optimization, if you kind of explore in the neighborhood of your optimum and you're in a convex body, the average position of these samples would be better as an estimate of the actual middle of the basin you're in. And that's what we can do here. We can do a bunch of estimates and then get the star, which is more representative of the middle of the basin, the actual optimum. The same for the red basin. And then we can combine kind of the best of both worlds. We both kind of get a better estimate of the basin you're in, and also ensemble those from different optima that are decorrelated more than within the same optimum. Okay, now I was describing the whole way a picture of a lost landscape where the basins are connected. Okay, so there are these two basins and you could move from one to the other on these connectors. They're hard to find at random, but optimization can allow you to find where they are. Okay, so that would be the dream of kind of the Bayesian optimization, I guess Bayesian optimization would be to extensively go from one initialization to the optimum, but then to cheaply traverse these connectors between different optima and sample a very diverse set of functions such that you can ensemble them afterwards. And that would be great because it would give you very cheap in terms of optimization time and very diverse set of functions to optima to do ensembling on. But it turns out what typically happens is that because these connectors are extremely small, so geometrically extremely constrained, the methods that kind of wander around and try to find a hole into a different basin typically get stuck within the single optimum. And if they do not get stuck, if you kick them out, let's say with using high learning rate, they effectively have to reconverge to the optimum, and they don't use these traversable connectors between the optima. So the benefit you were hoping for doesn't seem to be there. And so my picture of the manifold here is a bit misleading because it looks more like this cover of this great book called High Dimensional Probability by Roman Vershinin. So it looks more like a hedgehog with like really long spikes. And these spikes seem to be the things kind of connecting the optima together. And these spikes are extremely hard to find for the very naive Bayesian methods. And of course, the jury is still out whether some method will be able to kind of do that, to kind of explore, to utilize the fact that the set of optima seems to be interconnected together. But so far, the methods we compare to do not fare too well in this respect. And so this concludes my talk. I guess the takeaways are that understanding deep learning requires working on the high level of abstractions, because when you kind of go to the weights and biases, it's really hard to see what's going to happen on the high level when it's classifying an image, or on the semantically human level that we typically deal with. And on that level, the geometry of the lost landscape has surprising simplicities you wouldn't expect from a generic high-dimensional function. So we don't have to throw our hands in the air and say, well, it's too complicated, we can't say anything concrete. We can actually go in and empirically measure some of these things that I described, some of which in this talk. And the third point is that those simplicities imply a geometric model of the lost landscape that has implications for the Bayesian methods and their success or current kind of failure to live up to their mathematical promise in very big models and real data sets. Okay, thank you very much.
Thank you.